This lesson is entitled Derivative of Trigonometric Functions. In this lesson, we're going to discover the derivative of the sine of x, the cosine of x, the tangent of x, cosecant of x, secant of x, and cotangent of x. They will each be developed. And so that will greatly increase the tools in our toolbox and make the course become hopefully more interesting. Here are the tools we're going to need in order to discover these the derivative of these six trigonometric functions. We're going to need the definition of the derivative, which is f prime of x is equal to the limit of f of x plus h minus f of x over h as h approaches 0. We will need that. We'll also need the fact that the limit of the sine of x over x as x approaches 0 is 1, which we found to be a definition, or we considered it to be a definition in an earlier lesson. In an earlier lesson, we also found that the limit of the cosine of x minus 1 over x as x approaches 0 is equal to 0. And we're going to need that fact as well. So we'll need the definition of the derivative, we'll need this fact, and we'll need this fact. In addition, we'll need the fact that the sine of a plus b is this identity, the sine of a times the cosine of b plus the cosine of a sine of b. You should have had that in your earlier study of trigonometry, but you may have forgotten that, and we're going to refresh your memory and show you a use for that identity. And in addition, we need the fact that the sine squared of x plus the cosine squared of x is equal to 1. So we need a lot of tools in order to do this. That's not all. We need to know that the tangent is the sine divided by the cosine. The cotangent is the cosine divided by the sine. The cosecant is 1 over the sine. The secant is 1 over the cosine. And the cosine is 1 over the tangent of x. Now we say we, that's myself who's going to do these derivations for you. We'll need these in order to get the desired results. And you'll need to know these in order to be able to follow along to what's being done here. So let's begin by finding the derivative of the sine of x. That is, if f of x is the sine of x, find f prime of x. Well, if f of x is the sine of x, and we're going to use the definition of the derivative, then we need f of x plus h. Well, f of x plus h is going to be the sine of x plus h. So here's your definition of the derivative. Now let's substitute in for f of x plus h, the sine of x plus h. And for f of x, the sine of x, all of h as h approaches 0. Now, what we're going to do next is we're going to use this identity, the sine of a plus b, where for, in our case, a is x and b is h. So that means the sine of x plus h is going to be the sine of x times the cosine of h plus the cosine of x times the sine of h. Okay, now we still have that negative sine of x here, so we have to include that. That's all over h. Now, the next thing we're going to do is we're going to bring this negative sine of x forward up to this point here and move the cosine of x sine of h to the rear of the expression, which is what you see here. We have down here 1, 2, 3, 4. They correspond to these numbers 1, 2, 3, and 4. This tells you down here what we're doing at each step. Okay, so that in step 1, we used the commutative property. That's what allowed us to move the sine of x forward, and as you see here. Now, the next thing we're going to do, you see, we have the sine of x, cosine of h, and a sine of x. So we're going to factor out a sine of x from this expression. And when we do, we're left with cosine of h and minus 1. This we'll simply leave as is. Okay, so that's what's happened between here and here for step 2. Now, in step 3 and 4, here's what we're going to do. We're going to divide, separate this into 2 fractions. In other words, we're going to write sine of x cosine of h minus 1 over h, and cosine of x sine of h over h. But in addition, when we separate it, we're going to put the h under this term right here. Okay, instead of having it under the whole thing, we'll put it under this. And that's not violating any rules of fractions. And likewise, here where you have h under this part of the fraction, we're going to put the h just under the sine part. And in other words, make sure you understand that cosine of x sine of h over h and just cosine of x over sine of h over h are the same thing. In other words, cosine times sine all over h or cosine times sine over h are the same things. Now, if you've got that, you see we have a sine of x, but the h is going to 0. In other words, this tells me that h is my variable, not x. So as far as this expression is concerned, this sine of x acts like a constant. So we can simply consider this to be the sine of x times the limit of the cosine of h minus 1 over h as h approaches 0. So it's the sine of x times the limit of this. But this limit, remember, is equal to 0. If we go back and look here, remember, that's equal to 0. So what we're going to do is in the place of this, we'll put 0. So this becomes sine of x times 0. Now, likewise, since h is going to 0, and this is cosine of x, we can pull the cosine, move the cosine x in front, and we simply take the limit of the sine of h over h as h approaches 0. And if we go back, we remember that's defined as 1. And so we will write this as cosine of x times 1. Okay. So now the sine of x times 0 is just 0. And the cosine of x times 1 is cosine of x. And we're done. In other words, we started with the sine of x, and we're finding its derivative, and we have that it's cosine of x. Now, look how many tools from this page we used. We used the definition of the derivative. We used this fact. We used this fact. And we used this identity. So we used a lot of those tools in doing this particular problem. So we come to the conclusion then that if f of x is a sine of x, then f prime of x, the derivative, is simply the cosine of x. You need to know that fact. Before we go further, let's look at these 2 graphs. What you see in front of you, this is the graph of the sine of x. And this is the graph of the cosine of x. Why are we looking at these 2? Because when you have the sine of x, its derivative is cosine of x. That's why we're looking at this. Now, here's what we want you to pick up on. Remember now, this cosine of x is not only a function, it's the derivative. And what is derivative? Slope. So this is the graph of the function. This is the graph of its derivative, or its slope. Now let's see if that's true. What is the slope of this curve from here to here? Now, we're not asking you for a numerical value. We are interested in what is the sine of the slope. Now, the sine is positive from here to here, is it not? Now, The graph here is above the x-axis, which is the positive region. Remember, when you have an axis, that's that above the x-axis is where the output value is positive, and that's below is negative. So the graph is above the x-axis from here to here, and the slope is positive from here to here. Okay. Now, watch my hand from here all the way down to here. The slope of the sine graph is downhill or negative. Now here, the graph of the derivative of the sine graph, which is the cosine, is down below the x-axis. Okay, it's negative. And from here on, from here my hand on up, the slope of the sine graph is positive, and the graph of its derivative, which is a cosine, is above the x-axis in the positive territory. And we find that interesting, and we thought maybe that would be a picture way of you seeing that the derivative of the sine is indeed the cosine of x. Now, we're going to get mileage out of this later when we begin to be given the graph of a derivative and asked to interpret the original function. So this was not just done in folly. We got what we wanted, which is to show the relationship between the graph of the sine and the graph of its derivative, which is the cosine. But we will also get mileage out of this later in the course, but not today. Now, what's the derivative of the cosine of x? Well, we could do what we just did. There is another identity where the cosine of a plus b is the cosine of a times the cosine of b minus the sine of a times the sine of b. And we can, using the definition of the derivative, likewise, in the same manner we just did, show that if f of x is the cosine of x, then the derivative of it is negative the sine of x. But we're not going to do that because we really probably aren't going to hold you responsible for being able to do this, derive all of these formulas yourself. Some of them you will be asked to, but not necessarily these. It's certainly possible, but not as probable as some other things. And so what we wanted to do is we wanted to show you why we needed the definition of the derivative, and we wanted to show you all the tools necessary. So we did what we wanted to do with the derivation of the sine of x. We're not going to repeat that with the cosine. We're simply going to give you the answer. However, if you're an inquisitive type of person and would like to try this, that would be wonderful to see if you can indeed start with the definition of derivative and using this fact, come up with the fact that the cosine of x, derivative of cosine of x is minus the sine of x. That would be a wonderful workout and pay great dividends, and you should feel good about yourself when you find that you can do that. But we're not going to do that here. We're simply going to take it as a statement here. Now, we'll work the following exercise. If f of x is the tangent of x, what is the derivative? In other words, what is the derivative of the tangent of x? Now, we're not going to use the definition of the derivative. Okay, we're not going to use the definition of the derivative, but what we are going to do is we're going to use the fact that the tangent of x is the sine over the cosine of x. We come back here. Remember these that we need? We need that right now. In fact, we're going to need each of these in the subsequent frames. So let's go back to our problem at hand. We write the tangent as a sine over the cosine. Now, why do we not need the definition of the derivative? Because we can get the answer from here. You say, what do you mean? We know the derivative of the sine, do we not? It's the cosine. We just learned that. We know the derivative of the cosine. That's negative sine. We just learned that. And we learned the quotient rule some time ago. So we're going to use the quotient rule on this, which is denominator, cosine of x, times the derivative of the numerator, or the derivative of the sine is the cosine of x, minus the numerator, which is the sine of x, times the derivative of the denominator, the derivative of cosine of x is minus the sine of x, all over the cosine of x quantity squared. Okay, got that? Now this is cosine of x times cosine of x, which is cosine squared of x. And this is negative sine of x times the sine of x with a negative sign in front. That's going to be positive sine squared of x over the cosine squared of x. And now we're going to use that other tool we saw. We won't go back there to show you. We had written down that the sine squared plus cosine squared is 1. So we're going to use that fact here. Okay. And so it turns out that the derivative of the tangent is 1 over cosine squared of x. However, in most of the textbooks that we have seen, that is not how they write it. There's nothing really wrong with that answer. But they usually use the fact that 1 over the cosine is the secant, or the secant is 1 over the cosine, vice versa. So 1 over the cosine is the secant, so 1 over the cosine squared is the secant squared. And this is the more traditional way of writing the derivative of the tangent is secant squared of x. We encourage you to learn it that way, not this way. Okay. Now, this is a doable problem, and certainly within the scope of most courses. Don't be surprised if you don't run into a problem somewhere on some type of test where you're asked to show the derivation, or show that the derivative of the tangent is the secant squared, or however it might be asked. This is certainly something that you might be asked to do, so be prepared. The reason I say that, earlier we said we're not so certain you would be asked to use the definition of the derivative to derive the fact that the derivative of sine is a cosine. We can't guarantee that, but we are saying here that the likelihood of you having to do this particular exercise as an assignment is certainly within the parameters of the expectations of most calculus courses. So we have then, if f of x is the tangent of x, then f prime of x is the secant of x. So we have 3 formulas counting. We have that the derivative of the sine is the cosine. You need to know that. The derivative of the cosine is minus the sine. You need to know that. And now we have that the derivative of the tangent is the secant squared of x. And you likewise need to know that. Now, we're not going to derive the cotangent, because the cosine is the cotangent, is the cosine over sine. And we can use the quotient rule. So likewise, we can take the derivative of this thing. Okay. And just as we did with the tangent, which is sine over cosine. And when we do and simplify, we're going to get negative cosecant squared of x. So we're not going to work this one for you. You may be asked to do that in your class, but we're not going to do that here. We need to move on with the idea we showed you one, and the other is done roughly in the same identical way. So we have another formula. The derivative of the cotangent is negative the cosecant squared of x. Now we come to the secant of x to find the derivative. And again, we're not going to use the definition of the derivative. What we're going to do is we're going to use the fact that the secant is 1 over the cosine. And again, we're going to use the quotient rule. So we'll take the derivative of this using the quotient rule, which will be denominator, cosine of x, times the derivative of the numerator. The derivative of 1 is 0, minus the numerator, which is 1, times the derivative of cosine of x, which is negative sine of x, all over the denominator squared. That is the quantity cosine of x squared. Now, of course, this is 0, and this is minus. A minus is a plus, so we end up with sine over cosine squared of x. And that's certainly a correct way of saying that the formula for the derivative of the secant of x. However, again, textbooks are what they are, and generally speaking, that's not how you'll find the formula for the derivative secant written in most standard calculus books. What they do is they take this and they split this cosine into two parts, cosine times cosine, and say sine over cosine times 1 over cosine, right? Like that. This is tangent, and this is secant. And so it's tangent secant of x, okay? Now, there's a reason they're writing them like this. We're not going into everything, but it really does. It's much easier to remember this than it is to remember this. If you begin to look at the end, if you can see a pattern that will help you remember these formulas, you'll see that this is easier to remember than this. And that's why this is written this way. As was the derivative of the tangent was written as a secant squared. It's easier to parallel them with each other and find a scheme for learning them without using just rote memory. So the derivative of the secant is the secant of x times the tangent of x, and you need to know that. Now, this brings us to the last one, which is the cosecant, and we're not going to do this one, because it's done the same way, just as the secant is 1 over the cosecant is 1 over the sine. Again, that was one of our original tools. We're going to use the quotient rule here, and we're going to end up with this result, that the derivative of the cosecant is minus cosecant of x cotangent of x, and that completes our 6 derivative formulas. And you need to know them, and you need to know them fairly in rapid fashion, not doing a lot of thinking. And going to have to know these because we're going to later in the course have to, and we don't want to get too far ahead of ourselves, but we're going to have to know these real well for what we're going to do towards the completion of the what's known as the curriculum for a first introductory calculus course. So you want to know them well, just like you want to know your multiplication table well in order to do division. Okay, it's the same principle there. You can't do division without knowing multiplication, and you can't do what we're going to do near the end of this course without knowing the derivative. So we will help you with one thing. Notice though, notice this is a cosine and the cotangent and the cosecant. They each they're cofunctions, and their derivative is negative. So that might help you there in learning that. So keep that in mind. If you can see any other correlations on your own that will help you learn it, that would be great. But we'll leave it at that and let you figure those out for yourselves. Okay. Next, we're going to look at some examples using these 6 formulas. Why? Well, one reason is this will give you a way to learn these formulas without just memorizing, by using. But in addition, we're going to revisit some of the things we already know. Now, like what? Well, we're going to revisit the fact that the derivative of x to the n is n times x to the n minus 1, the power rule. We're going to revisit the fact that the derivative of e to the x is e to the x. We're going to revisit the fact that you have a quotient rule. We're going to revisit the fact that you have a product rule. We're going to revisit the fact that there's a second derivative. And we're going to revisit the fact of writing the equation of a line tangent to the graph using our new formulas. So let's begin with that. So first example is this. Find f prime of x given f of x is x squared sine of x. So let's begin. This is a product, so it'll be the first x squared times the derivative of sine of x, which we now know is the cosine of x, plus the second sine of x times the derivative of x squared. Power rule is 2x. We'll clean this up a little bit. by at least moving the 2 in front here. So we have x squared cosine of x plus 2x sine of x. And that's a good answer. But we could factor out an x and get this answer. And that's a good answer. Which is better? We're not going to decide on that, but we just encourage you to realize that they're the same. Okay? And we'll leave that problem as been completed. Let's go to example 2. This we want to find f prime of x, and given that f of x is a tangent of x over x cubed. Now, what's this problem going to show us? Well, it's going to bring in the fact that the derivative of the tangent x, got to know that. So this will help us get started learning that. And we're going to have to review the quotient rule, which is denominator x cubed times derivative of the tangent. New rule, derivative of the tangent is the secant squared of x minus the numerator, tangent of x times the derivative of the denominator, which is 3x squared, all over the quantity x cubed squared. Okay. Now, we'll clean this up a little bit. This is going to be x cubed secant squared of x, and we'll bring the 3 and the x squared in front, like so. And remember, x cubed squared is x to the 6th. Don't be tricked into thinking it's x to the 5th. No, you multiply exponents. It's x cubed times x cubed, and x cubed times x cubed, you add exponents, is x to the 6th. I'll also make sure. That's a good answer. However, see, we have an x squared and we have an x cubed. We can factor out an x squared, and that's a good answer. But then you see you have an x squared and an x to the 6th, and can we not reduce this x squared? This is, x to the 4th times x squared, so the x squared cancel. However you want to look at it, this is, and this is another answer. Answer, answer, answer. Different ways of writing the same answer. Let's look at example 3. What's different here? Quotient rules still. We really need to practice the quotient rule, and we are going to do that in these exercises because most students find the quotient rule to be really troublesome. So we'll try to hammer its importance by working problems. And we're introducing now the secant, which we haven't used, and e to the x, which we haven't used. So let's begin. Denominator, secant of x, times the derivative of the numerator, which is e to the x, minus the numerator, which is e to the x, times the derivative of the denominator. Remember, this is secant of x, tangent of x, all over the quantity secant of x squared. Okay. Now, we kind of rewrite this a little bit better, and we notice that we have an e to the x here. This is not a bad answer right here. Okay, right here. You could stop right here, but we do have a secant of x here and a secant of x here, and we have an e to the x here and an e to the x here. And what we can do is factor out an e to the x secant of x. That's all we've done here, over secant squared of x. And then, since I have a secant of x here and a secant squared, can I not cancel, giving me just a secant of x here and getting rid of the secant in the numerator? Answer, answer, answer. Okay. Let's move to example 4. Another quotient rule. Now, this one's harder. It looks harder, it is harder, but it turns out to be nicer. Looks hard, but turns out to be a nicer problem. And let's begin. We're going to use the quotient rule. Denominator, 1 plus the cosine of x, times the derivative of the numerator. Derivative of the sine is the cosine, minus the numerator, which is the sine of x, times the derivative of the denominator. Derivative of 1 is 0, derivative of cosine is negative sine of x, all over the denominator squared, which we're writing here. Now, if we multiply this out here, distributed, we get cosine times 1 is cosine, and cosine times cosine is cosine squared, and negative sine times the sine of x with a negative sign in front of it is the sine squared of x. Okay? Now, sine squared of x plus cosine squared of x is 1. That's one of our tools from the earlier page. I think we've used almost every one of those tools. We need that here. Sine squared plus cosine squared is 1. Okay, so this becomes 1 plus a cosine of x. Cosine of x plus 1, or 1 plus a cosine of x. Now, all over 1 plus a cosine of x squared. Now notice, 1 plus a cosine of x here, 1 plus a cosine of x squared here. Can we not reduce this to just 1 over 1 plus a cosine of x? So this looks to be horrible, but it's not. It's a nice answer. But there are a lot of places you can go wrong with this problem. First of all, the quotient rule. And then the fact that when you use your distributive property, you've got to get that right here. And then you've got to know that minus times a minus is a plus. So you've got to get that right. And then you've got to know that sine squared plus cosine squared is 1. So you've got to get that right. And then you've got to reduce it. So for a person that knows how to do all of that, this is not a bad problem whatsoever. Now, the thing you have to do is relax. You work in the problem and have confidence. Do you know the quotient rule? You've got to know the quotient rule, people. And do you know your formulas? That is your 6 derivative formulas plus your power rule and your derivative e to the x. And then you've got all the tools you need. And at least it can get you to the raw form of the answer. Okay, the raw form of the answer. See, if you don't know the quotient rule, you're not going to get here. If you don't know the derivative of sine and derivative of cosine, you're not going to get here. But if you know those facts and the quotient rule, you can get here. And this is not a bad answer. It's just that this is cleaner, even cleaner, and cleanest answer. And that's about all we can say about that particular problem. Example 5, we want the second derivative. We told you that was one of the things we're going to do. So we're given y as the cosine of x, find the second derivative. Well, the first derivative of cosine is negative the sine. And then the derivative of negative sine, well, the derivative of sine is a cosine with a negative sign in front of it, is negative cosine. Now, that is pretty easy. In fact, we found so far in this course, every time we've had to take a second derivative, there's not much work to it. Let's go to example 6. And let's see if we can quash that myth. That is that the second derivative is always easy. Let's look at this. Y is equal to e to the x cosine of x, find the second derivative. Well, product rule. First, e to the x times the derivative of second. The derivative of cosine is negative sine of x, plus the second cosine of x times the derivative of e to the x, which is e to the x. And we can maybe clean this up a little bit by writing this is minus e to the x sine of x and e to the x cosine of x. At least we get the negative sign out front. Now we've got to take the derivative again. And you can go right here and take the derivative of this. The only thing is, you got to take the derivative of this product. And then you've got to take the derivative of this product. In other words, you've got to use the product rule twice. So you've got to be careful. However, we can avoid that double use of the product rule by recognizing that you have an e to the x here and a negative e to the x here. Let's factor out an e to the x. And when I do, I get cosine of x minus sine of x. So we have only one product. Now, take the derivative of this. That's the first, e to the x times the derivative of this. Derivative of cosine is minus the sine. Okay, and derivative of the sine is cosine with a minus sign in front. So we have that. That's the first times the derivative of second, plus the second, cosine of x minus sine of x times e to the x, derivative of e to the x, which is e to the x. So we've used a product rule again. Now, notice we have an e to the x here and an e to the x here. So e to the x here, excuse me, e to the x here and an e to the x here. Let's factor out an e to the x from each of these terms. And when we do, we're left with a negative sine of x, negative cosine of x, and a positive cosine of x, and a negative sine of x. Now, negative cosine, positive cosine are opposites, so those terms vanish. We're left with a negative sine of x and another negative sine of x. We're left with two of these, two negative sine of x's. And let's get the negative sign out front, and we do, and there is our answer. Okay. Now, had we done it here, we would have gotten the same answer. And I don't know, it's all in how you see a problem. If you see it like this and you want to go in and tackle it, do. If you see this, do. If you perceive that this is easier than taking this, it's all in how you perceive it. If you think it's easier to do it one way than the other, you do it that way. We're not going to instruct you which way to do it. We chose to do it this way, and we could have chosen to do it the other way, I guess, as well. So that completes that problem. The last three problems have to do with writing the equation of tangent lines. So let's do this. We have the cosine of x is our function, and 0, 1 is our point. Notice when x is 0, the cosine of 0 is 1. If you don't know your trig functions, such as sine and cosine of things and tangents, things like 0, pi over 2, pi over 6, pi over 4, pi over 3, work on those up until you do know them or have confidence. Check yourself out with your calculator. Cosine of 0 is 1 if you use your calculator to verify that. Now we want to write the equation of the line, tangent to the graph. So we need derivative. We've got the point, right? 0, 1. So we need derivative. That's negative sine. When you put in 0 into negative sine, the sine of 0 is 0. So minus 0 is 0. So the slope is 0. So the slope is 0. And here's my x and y coordinates of the point. So I'm going to use the point slope formula that we talked about earlier. And in the place of y sub 1, we'll put 1. Okay, and we do. And in the place of x sub 1, we'll put 0. And we do. And in the place of m, we'll put the slope, which is 0. Now this vanishes. So this is just y minus 1 is 0, or y is 1, and there's my answer. There's my answer. If you'd like to check yourself out with your calculator, type in cosine of x under what, maybe y1 on your calculator, and then under y2, put your y equals 1, and see if indeed this line does not touch the graph of cosine of x at 0, 1. It does, okay? But anyway, if you want to check yourself out to make sure, that's an easy one to do it on. Now we have the sine of x, and that point's pi over 6, 1/2. And it turns out the sine of pi over 6 is 1/2. So, but if you don't know that, sine of pi over 6 with your calculator should come up as 0.5 to verify that. So again, if you're weak in your trigonometry, work on learning these and let your calculator help you learn them rather than letting your calculator just do them for you. It depends on the situation. Many of the textbook problems are written so that you have to know the exact value. Others will let you use decimals, approximations, and so you've got to be prepared to do whatever the problem calls on. But at any rate, we have our x coordinate, we have our y coordinate, do we not? So we can basically put in for our x coordinate pi over 6 and for our y coordinate 1/2. Now all we need is slope. That's derivative. And the derivative sign is a cosine, and the cosine of pi over 6 is the square root of 3 over 2. Or we're not going to use the decimal equivalent. We'll use that. Now, I would suggest you leave your answer like this, and I think most textbooks will. However, we have asked here to put it in y equals mx plus b format. Why? And the only reason we're asking you to do that is so if you want to graph it, in other words, if you want to see this is indeed the function you've got is indeed tangent to the sine of x at this point, you would need this to do that. But that's the only reason we've done that. It's not really difficult. You've got to get some common denominators. This is your slope. This uh, glob here happens to be your y-intercept, but it's a number. It's a number. Pi is a number, square root of 3 is a number, 6 minus a number is a number over 12 is a number. It's just not a nice integer, is it? So much for example 8. So a little bit harder now. Let's go to our last example. We're given the equation tangent of x, and we're choosing x equals pi over 4 for this one. Pi over 4 is a nice choice for a number here, believe it or not. So we have our x coordinate, it's pi over 4. We need our slope, so we'll take the derivative of the tangent is the secant squared, and we want to find the slope. So f prime of pi over 4 means secant squared of pi over 4. Now, do you know what the secant of pi over 4 is? Well, let me help you here. The secant is 1 over the cosine, and the cosine of pi over 4 is 1 over the square root of 2, or square root of 2 over 2. Let's think of it as 1 over the square root of 2. That will help us here. So the cosine of pi over 4 is 1 over the square root of 2. The secant is 1 over the cosine, so 1 over the square root of 2 is just the square root of 2. So the secant of pi over 4 is the square root of 2, but we've got the secant squared. So if the secant is square root of 2, the secant squared is the square root of 2 squared, which is 2. How nice. That's my slope here. Okay, so I have my x coordinate and I have my slope, but I don't have my y coordinate, but that's going to be easy enough. How do you find your y coordinate? You put your x coordinate into the original function, and the tangent of pi over 4 is 1. Pi over 4, that's radians, but in degrees, pi over 4 is 45 degrees. If you have a right triangle and one of the acute angles is 45 degrees, the other one's got to be 45 degrees. And so it's an isosceles triangle, which means the two legs are equal, and the tangent, remember, is the opposite side over the adjacent side. Doesn't involve the hypotenuse, so it's 1 over 1. And so this is just how you can, we're just playing mental gymnastics with what we know from the past. So we're talking a lot here, but this is the last problem. But we want to show you how you can know this is 1 through what else could it be type of thing. Okay, so now wrapping this up, we have our x coordinate, so we put that in here. We now have our y coordinate, we put that in here, and we now have our slope, we put that in here, and you may stop right here. That's a legitimate answer. However, if you want to graph it, you're going to have to solve for y, and so the slope is 2, and this is your y-intercept. And so, and that's going to be a negative. See, pi is 3.14, so 2 minus pi is going to be a negative over 2, so it's going to be a negative. Just rambling on here. We are at the end of this lesson. So I hope this has been helpful. Of course, the whole thrust of this is two-pronged. The first part of it was to show you, actually three-pronged, show you how to get the derivative rules, okay? The 6 derivative rules of the trig functions. That was the first thrust of it. The second was to find those 6 derivative rules for you to memorize. And then the third prong of this lesson was to practice things from the past, okay, to review. And that's one of the things we constantly do in this series of lectures. But the main thing out of here is if you go back here quickly to a perfect, that's the page you want to concentrate on. That's where the real meat of this lesson is and what you're going to have to learn. So if there's one page in this entire lesson, go back to this and make sure you are able to give this back in pretty rapid fashion. So this completes this lecture.